I'm Alex. I'm here to talk to you about spinning defects in the O2N model, which is based on some upcoming work with Peter Kravchuk. So normally when we look at a defect CFT, we expect the conformal group to be broken to, if it's a p-dimensional defect, we expect this conformal group to be broken to the conformal group along the defect times the group of transverse rotations around the defect. This project came essentially from going, what if we try to find a defect where transverse rotations around the defect are not a symmetry of this theory? And so in this talk, I will describe such an example in the O2N model. So probably be worth noting that there are a couple of examples of defects like this. We've taken to calling them spinning defects because, you know, a spinning operator transforms non-trivially under rotations. So we know that Gukov-Witten defects are an example of such defects, as are vortex loops in ABJM. But we want to create a non-supersymmetric example in a fairly simple model from a CFT point of view, and so that's what I'm going to talk about today. So how can we create such a model which we believe will have conformal symmetry along the defect, but will not be symmetric under transverse rotations? Essentially, the way that we try to accomplish this is we find an operator with spin, so one that transforms non-trivially under transverse rotations to the defect. We try to find such an operator in a defect CFT. We look at the RG flow triggered by it, and we look at the IR point. So how can we get a DCFT with a relevant operator with spin? Our starting point in the critical O2N model is looking at a monodromy defect. So when we do this, we keep the regular action for the O2N model. So we have, so I'm going to write this in terms of n complex scalars. So I is going to range from 1 to n. So we've got our usual action. And when we add a monodromy defect, what we do is we take a codimension 2 defect, and what we say is that as we rotate our field around this defect, it transforms non-trivially. If we transform it all 2 pi around this defect, then it picks up a phase of e to the 2 pi I v. Okay, so without loss of generality, let's take v to just be between 0 and 1. So essentially what we're saying is we're not going to add a defect term to our action. We are just going to say that when you go around the defect like this, you pick up a phase. So one consequence of this is that the defect operators in this theory, which you will get in the bulk to defect OPE of phi, will have, sorry, there should be i's here, will have spins which are no longer integers. They are now in z plus v. Essentially, the reason for this is because spin is normally quantized to be in the integers because you need your fields to be periodic, but instead we actually need them to pick up a phase, so instead we want them to transform with non-integer spin. So this model has been studied before. In particular, for our purposes, it was studied by Giombi and some collaborators in 2021. And they found the scaling dimensions at large N of the first few of these operators. And I've plotted them in this plot, which does not yet have any labels. But so we can look as a function of v, between v is 0 and 1. So you've got this line here is the scaling dimension of psi v. This is the scaling dimension of psi v minus 1. This is the scaling dimension of psi v plus 1. And this is the scaling dimension of psi v minus 2. Now, the interesting thing about this for our purposes is that this is in 3 dimensions, this plot. And that means that since our defect is codimension 2, the defect is 1-dimensional, and so we've always got either 1 or 2 relevant operators here, okay? So essentially our goal in constructing these spinning defects is just to take our action and look at the RG flow triggered by one of these operators. This is symmetric, and that's essentially because picking up a phase of v is kind of almost identical to picking up a phase of minus v, but we've required v to be between 0 and 1. So yeah, the two ends of these plots are essentially identical, and flipping this around just corresponds to interchanging phi and phi bar. So yeah, so what we are going to look at is adding to our action a defect term, which is the integral along the defect of the real part of psi v, so of this operator. So the other thing to note about this plot is that there is this point where this operator psi v becomes irrelevant, and we are going to call that v star. In d equals 3 at large n, v star is roughly 0.617, and in 4 minus epsilon at any n, v star is equal to 1 minus epsilon over 2 plus something, something, something. So this is in fact a plot of v star as a function of the dimension at large n.
So is this a different way to get the same monodromy defect?
No, this is going to construct a different defect in the IR of this flow. So yeah, I'll come to that in a minute. So
why couldn't you get a UN transformation? Why can't you get a UN transformation instead of just a phase?
You can. We're just looking at this case. Yeah. So one nice thing to do at this point is to just think about the symmetries of this theory. So we can look at the symmetries in the ON model of a trivial defect. A monodromy defect. And the IR fixed point of this flow, which I'm calling a spinning defect. And so first of all, we've got the space-time symmetry. And so for the trivial defect, we've obviously still got the conformal group. When we add a monodromy defect, we break this down to the normal group left over in the DCFT, so SO P plus 1, which is D minus 1, 1, times transverse rotations, so SO2. And in this defect, because this operator is going to transform non-trivially under rotations, we're just going to get SO D minus 1, 1. It's worth noting, I'm assuming here that V is not equal to 0 nor a half, because those are special cases from this point of view. We also have the internal symmetry, which obviously starts off being O2n. when we introduce the monodromy defect, we have to package what would be 2n real scalars into complex scalars. And so this breaks the symmetry down to un. And when we do this, we have to choose a direction in the internal space to perturb by. So this further breaks the symmetry to un minus 1. The final thing that's worth noting from a symmetry point of view, though, is that there is one other symmetry which becomes present in this, which is a combination of one of these internal symmetries and one of these space-time symmetries, which essentially corresponds to sending phi. So if we do a rotation from theta to theta plus delta theta, and we also send phi to e to the minus I v delta theta, then essentially this mode will pick up a bit of a phase from the rotation, but that will be cancelled out by the rotation in internal space of phi. So we have got one extra symmetry here. So it's not the case that rotations are just broken in the whole thing. There is a combination of a rotation and an internal symmetry which is preserved. Okay, so now I'm going to talk about how we solve these models and the results that we get. So we've got this plot, which is v star as a function of v. So it starts at a half in d equals 2 and goes up to 1 in d equals 4. This plot is at large n because that's where we have the general results in general dimensions about this. And the operator should be relevant anywhere under this curve. So one thing that we will do is we will get a large n result for this theory. And we will find operator dimensions and things at large n. But there are other ways in which we can also study this system. So, for example, if we let v be very close to v star, so along here, then the operator is only weakly relevant. And so we can look at this through the lens of conformal perturbation theory. We also have the case where d is approximately 4. So d is 4 minus epsilon, where we can use 4 minus epsilon techniques to get some idea of what the solution looks like as we approach this limit. So what we're going to do in this upcoming work, and what I hope to explain a bit in this talk, is the results we get in these and how they correspond to each other. Any questions at this point? Okay.
Sorry. So when you are very close to this star,
Yep.
you understand correctly that you also have another relevant operator, which is the sine e minus 1?
Yes, we may do. There are 2 relevant operators in this range, and there is only 1 relevant operator here and there. But we're still just perturbing by one of them.
By some symmetry that prohibits these other terms to be generated?
Yes. I mean, this internal symmetry is dependent on what v is. If we tried to perturb by this operator, we would get this symmetry, but with v minus 1. Yeah. Okay. So I'm going to be a bit sketchy about this since it's a half-hour talk. But to look at these results at large n, oh, sorry, there's one more thing I want to point out about this plot, which is in the case where v equals 0, we have no monodromy, and in the case where d equals 3, we have a line defect. And in this case, this is just the magnetic line defect which has been studied by various authors in various cases. And so that's another good check that our method is working well, is to check that our results agree with this. So what we do to look at this at large n is actually we generalize the results from Cuomo, Komorgodsky and Mizey's paper from 2021 about this magnetic line defect, we essentially take the techniques that they used to solve that model and we extend them to be viable anywhere in this space, but at large n. So essentially the way that that works is, first of all, we perform a Weyl transformation from RD, where we defined this, across to ADS D minus 1 across S1. And this has been done in a bunch of works, but the nice thing about this, well, there are a couple of nice things. The first thing is that conformal transformations become ADS isometries. And so if you write down an action checking that it is conformally invariant, it's just checking that this is invariant under ADS isometries, which is quite nice and easy to do. And the other nice thing is that the defect gets mapped to the boundary of ADS. This means that adding a defect term to your action just corresponds to adding a boundary condition to your fields in here. And this has been used to great effect in a variety of works, including the work of John B. that I got that plot from. But in particular, it was used here. So essentially what you do at large n is you take this action, you do your normal things, you do a Hubbard-Stratanovich transformation, you expand at large n, you impose an appropriate boundary condition, you impose appropriate monodromy, because we've now got monodromy, and you can get some results about the theory. So in particular, when we do this, we introduce a Hubbard-Stratanovich field, which roughly looks like phi bar phi. And we can calculate its two-point function. And from this, we can look at what operators are exchanged in this two-point functions. So we decompose it into ADS D minus 1 cross S1 Laplace eigenfunctions. And we expect poles in that to correspond to the scaling dimensions of exchanged operators. So we can do this, and we find the scaling dimensions of the first few the first few operators to be exchanged in this, and we get their scaling dimensions, and we can plot them as a function of v. So this is in d equals 3 at large n. So we have to cut our graph off at v star, because that's where this operator stops being relevant and this RG flow stops being well defined. But essentially we get one operator whose scaling dimension approaches 1 as we go here, and we get another operator whose scaling dimension goes a bit higher, 1, so this starts at about 1.5 and this starts at about 2.5. One interesting thing is we've got this case which I excluded here, which is v equals a half. And one nice thing that we actually see numerically from this result is that when v equals a half, the scaling dimension of this operator is equal to 2. Okay? Now this is obviously to leading order in large n, but it's interesting. Another interesting thing that happens with this operator is its OPE coefficient in that limit goes to 0. So that suggests that this operator is possibly an operator which is allowed to be exchanged in this function when we have the un minus 1 symmetry. But when we've got v equals minus a half, the monodromy we impose on our fields essentially becomes phi goes to minus phi. So we don't have to work in terms of these complex fields anymore. So you get, in this case, an O2n minus 2 symmetry. And so that suggests that this operator can't be exchanged in this two-point function if we have that greater symmetry. So how long have I got? 10 minutes. Okay, so as I say, we also look at this same setup in other pictures as well. So for example, in conformal perturbation theory. So the key point here is that we're looking in the UV, where our defect is the monodromy defect, and we can look at the scaling dimension of the operator we are adding. Just realized these all look like V's, that's UV. So we assume that we are close to marginality because V is almost at V star. And so we say that this scaling dimension is D minus 2 over 2 minus something small. Okay? From that, we can... Sorry? Because I made a mistake. Better? Some people just insist on me writing the right formulas for our paper. So anyway, we can see from this that the beta function, as a function of this coupling, should look like, so at a fixed point, so the linear term should be 0. We should have, sorry, not the linear term, the constant term. The linear term should be minus delta h, and then we can suppose that the next term is a quadratic term. And if we assume this, then you get a beta function which looks like a parabola. And if I could draw a parabola well, you would see that the gradient here is, so beta prime of 0 is minus delta, but by symmetry across this axis, at the other fixed point, beta prime of h star is plus delta, okay? So what that tells us is that if we are in this situation, delta V in the IR should be given by D minus 2 plus delta. Now, in one of those sentences, I used the word if this were true. Essentially, it turns out this quadratic term comes from an OPE coefficient which vanishes in this theory, so we actually get a cubic term as the next order in here. And if you go and you actually work out where the zeros of this plot are, what you find is that the result of this is actually that beta prime of h star is equal to 2 delta. And what that means is that this scaling dimension should be d minus 2 plus 2 delta. And so one thing we can do to check our results in the large N is we've got this operator, which should correspond to psi 1v as we approach this, and we can look at what is the limit as v goes to v star from below of delta IR minus d plus 2 over delta uv minus d plus 2. And what we find is that this is indeed minus 2, as you would expect by looking at these two scaling dimensions. So what we find is that the conformal perturbation theory suggests that we have indeed identified the correct fixed point in this picture. And that's good, because it would be concerning if that weren't the case. So finally, we've got d equals 4 minus epsilon. Now this is a little bit trickier to study, essentially because for a generic point along here, our defect coupling is not small. And so that is a problem if you want to use perturbation theory. So we get around this by not using perturbation theory. Very innovative. So essentially what we do is we look for a classical solution for phi, which we can write in terms of coordinates y along the defect, theta, which is the angle around the defect, and r, which is the distance away from the defect, and we look for a solution which has the correct monodromy, so e to the I v theta times r to the minus 1, because we know the bulk scaling dimension to leading order in 4 minus epsilon is that, times some constant which can depend on v. And what we do is we note that away from the defect we've still got the bulk equation of motion, and we see if we can use this to constrain c of v. And what do we find? Well, we find that c of v is equal to some constant times 1 minus v squared times n minus 4. And once again, fortunately, in this large n calculation, we can also calculate this, and we find that this is the same dependence on v, and is another sign that things are going well. So one final thing that I think is interesting to note about this plot is that there is actually this region around here where both of our couplings are small, because we're in 4 minus epsilon, so the coupling lambda is small, and we are near v equals v star, so the defect coupling should also be small. So that means that you can actually just use regular perturbation theory in this region, and one thing you could do there is you could try to see what happens if you expand this and then look at what you get in d equals 3, v equals 0. And then hopefully the results should be comparable to what other people have got looking at the magnetic line defect. We have not currently done this, but it'd be interesting. So that's one of our future directions for work here. Another interesting thing, so one of the reasons we started working on this was because in a previous work with Peter and also with Ritam Sinha, we were looking at Weyl anomalies in DCFTs. And one thing is, if you break these transverse rotational symmetries, in 3D with a line defect, there is actually a Weyl anomaly term you can get. So one question would be, does this defect have that Weyl anomaly term? Since I've not mentioned this until now, you might be able to guess the answer is no. The reason essentially is because it involves an epsilon tensor, and so your theory has to break parity, which ours doesn't. And so it would be interesting to find a spinning DCFT with a Weyl anomaly. And all in all, in general, it would just be interesting to see whether there are a wide range more of spinning defects that you can construct, or whether it really is just a few examples like this in Gukov-Witten. But I still think this is an interesting class of defects because it's got these interesting special cases where you get a monodromy defect or the magnetic line defect, but it gives you this tunable parameter v, which lets you have all these interesting expansions, which is quite nice. Yeah, I think that's about all I wanted to say. So thank you for listening. Thank you to the organisers for inviting me, and any questions? Yes.
So in this picture, what happens to the displacement operator? Because normally for the monodromy, you can find it in the OP of psi v and psi v minus 1.
Yep.
But now I guess transverse rotations.
Sorry,
are
do you
not
mean
preserved.
in this picture?
Yeah, exactly.
So this is a plot of the kind of spin zero operators. We do also find that the displacement operator is exchanged and it has scaling dimension 2. So it does appear and it seems to behave
Okay,
normally.
and anomalous dimensions vanish to first order. and
Yes.
everything. Okay, great.
Anything else?
So in this plot for the cubic beta function, so
Uh-huh.
there is another fixed point, like for H star negative.
Yes.
So what is that supposed to be?
So yeah, essentially, I've rubbed out the action now. But essentially, this is even actually true in the magnetic line defect. Your beta function is just an odd function, and there are two fixed points with either sign of this coupling, and they are both attractive fixed points, and they essentially work the same except some of your signs are flipped. So yeah, that is a thing that happens. But this is just a symmetric plot, and so there are two fixed points. We've just chosen one arbitrarily.
It has the same symmetries in the IR.
Yeah.
of the-
And they're the same fixed point. This always happens when you have, when the flow breaks a symmetry, there is a.
Whenever you have a fixed point which breaks part of your UV symmetry, you can apply UV symmetries and get other fixed points. That's always true. And there's like, you might think that there is a manifold even in some cases of fixed points, but they're not actually different theories. They're all the same theory.
Yeah, you can actually even do it, so that corresponds, flipping the sign of the coupling corresponds to inserting a -1 into the defect term. But you can actually insert any phase in here. And so if you plotted this as a function of a complex coupling, H star, what you'd find is that, that there's a circle of these fixed points that you can go around. Yes?
Can you realize these defects in lattice systems?
Probably. I don't know. You can, so I think there are lattice results for the magnetic line defect, which means you can realize this point. There are, I think, lattice realization of monodromy defects, I think. So you can probably get this point. I haven't thought about it, to be honest, but I would guess so. I don't see any reason why not.
Thanks.
Where did you use large N in this analysis?
In one of the bits I kind of didn't explain, but we do Hubbard-Stratanovich transformation, and we do a saddle point expansion, and the 2-point function that we are expanding to get these operator dimensions is the 2-point function of that Hubbard-Stratanovich field. Yeah, so that's how we use it.
Can you explain your question? I mean, you've done some calculations at large N. In what sense?
Well, the talk started by saying it was large N, and then the calculations were sort of not too explicit, and it wasn't clear where large N entered into those calculations. Like if you were to, so I think I just never saw a large N mentioned again after over there. So I didn't.
Probably didn't write it and just said it quickly when I was going through it. But yeah, we use, when we get this action, we do a Hubbard-Stratanovich transformation. And yeah, that's how we control the large N.
I mean, okay, maybe to ask a variation on the question, if you were, I thought that at some point you were doing some limits close to the free theory, in which case you wouldn't need large N. You could just use perturbation theory. So it just wasn't obvious when you needed large N. Do you always need large N? So what could you do with at finite N?
You can use large N to understand anything on these plots. If you are near one of these limits, you can use one of those alternate descriptions. But you know, if we want to look in d equals 2.5 at v equals 0.25, then yeah, we don't have any way to study this without an expansion parameter. So we look at large N.
Okay, thank you.
Maybe that's all.
Question. Let's thank Alex again. Okay. And yeah, we should reconvene in 10 minutes. Okay, so we have time for a coffee. thank you very much. Let me start by thanking the organizers for giving me this opportunity to present my work here in Sao Paulo. Today, I'd like to talk to you about some work I did recently in the last year and a half, together with Gianfranco Fortan and Witold Skiba. We already have 2 papers out, and the third is appearing soon, about basically fundamental aspects of the Virasoro algebra, some fundamental objects. So this talk basically sits at the intersection of the 2 meetings happening here in Sao Paulo at this moment. Yeah, it is indeed very fundamental objects because I'm talking about Virasoro. What is Virasoro? I'm sure all of you are familiar with it, but it's the symmetry algebra that underlies 2-dimensional conformal field theories. In fact, 2D CFTs enjoy a symmetry represented by 2 copies of Virasoro. We're going to focus on just one because understanding the representation theory better of Virasoro will, of course, help us understand better the representation theory of fields relevant for 2D CFTs, and then help us get tools which we can use to bootstrap, possibly, or to expand correlators in 2D CFTs in general. So I'm going to focus on 4 results. It's quite ambitious for a half-an-hour talk, but maybe the last one it's like a bonus. If I have enough time, I'm going to mention that. Otherwise, it's not. But sorry? Sorry about that. I will mention that. But now, what are the 4 results? The first result is an expression for the resolution of the identity for Virasoro representations. Once one has a new expression for this object, one actually directly gets an expression for the Virasoro P, which can be translated into a new expression for Virasoro 4-point conformal blocks. And these objects are actually eigenfunctions of a new object that we constructed, an infinite order operator constructed out of Virasoro generators that commute with all of the generators of Virasoro, in fact. So this is actually quite new. Now, it is hard to put everything together in 1 hour, especially making it digestible for the majority of people, hopefully. But in order to help everybody follow, I'm going to just have a very quick review of Virasoro representation theory, basically. It's very basic stuff. But there is an operator state correspondence in 2D CFTs. We will focus just on states, but anything that I'm going to claim about states, one can translate it to fields for 2D CFTs. We parameterize the central charge in this nice way that comes from Liouville theory in terms of this B object. So every time you see B, think about the central charge, either B or C. And just lightning reminder, states can either be primaries that have a very well-defined conformal weight or descendants. The reason why I'm talking about this is because descendants, for descendants, we use this kind of notation. We have a basis for descendants. We use a Greek label, mu, to basically stand for a whole Young diagram, or analogously, a whole integer partition. This provides a basis for states because there is a unique way in which you can order stuff in ascending order. So every time you want to write down something in a basis of descendants, you can just write down stuff in an ascending order like that. OK, a descendant has a well-defined level, which is just the sum of all of the indices that appear there, so all of the sum of the indices of generators. And another object that we're going to need throughout the discussion is the notion of singular vector as well. Singular is the same thing as a null vector, is an object that is a descendant, but quote-unquote behaves as a primary. What I mean by behave as a primary? Well, I mean that if you act with a positive mode of the Virasoro algebra on this object, on this descendant, you're going to get some simple 0, like of the 0 modes of the Virasoro algebra, L0 minus HRS. The fact that it's a simple 0 is important, actually, for what's going to come later, that you can evaluate then, and it's equal to 0. But a simple 0 can be eliminated by simple poles. That's why it's important to highlight that. But yeah, these singular vectors are parameterized by 2 numbers, r and s. The level of the singular vector is r times s. And the expressions are in general, well, known by now, but they're very complicated. So if I'm starting by promising some expression using singular vectors, you may already start to decouple, thinking, OK, it's going to be impossible to use them explicitly. But it's going to be perhaps surprising to see that we can indeed do so, and we can get some concrete expression for Virasoro 4-point blocks which are usable. And I think they may also be quite efficient numerically. We're going to get there. Now, Why am I talking about singular vectors? I'm talking about them to introduce one object, which has a fancy name, but it's actually very simple, which is called the Shapovalov form. And the Shapovalov form is what detects the presence of these special representations. Like you can think about the singular vectors are shortening conditions if you want. And the way to detect them is by defining some kind of scalar product, if you want, of states within a Virasoro representation of the following form. This is not ordered, so one can just change the order of the two objects. One gets some matrix of 0 modes, because all the positive modes annihilate the state on the right, the negative modes annihilate the state on the left, and we get this object here in the middle, which is what we call the Shapovalov form. Okay? It is simply the Gram matrix within a representation of Virasoro. Okay? It's nothing fancy in principle. Why do we care about that? We care about that because it's a central object for all the results that are going to come, including the Casimir operator. Now, are there any questions so far? If there at any point, please feel free to interrupt. But L is the level, exactly, yes. So the sum of all integers, that one. These are, I suppose them to be of the same level, otherwise it's going to be 0.
I'm not sure, but I suspect it's Shapovalov.
Shapovalov, sorry. Like the pronunciation you mean, or the writing? Yeah. Yeah, I'm going to try my best. I'm sorry. Now, why do we care about that? We care about that because the first result, which is the starting result from which everything else can come after, is defined in terms of the inverse of this object, like the resolution of the identity is an object that if you act on a certain state, it's going to return you the same state, simply. It's a very trivial object. It has a form of this type, some L greater than 0, L minus mu, H. This is all known in the literature. I'm not saying anything special. I should rather say L0, mu nu, L nu here. And why should you care about this object? From this object, you can derive, like, straightforwardly, if you have it, for example, the Virasoro OP. Like the Virasoro OP is nothing but an insertion of a resolution of the identity. You can see that as the sum over the spectrum. You inserted the identity next to the product of two fields. Okay, so this is one way in which you can be motivated in understanding why do we want to determine this object. Of course, this determines the OP. It can also determine the conformal blocks. So that's very useful for Bootstrap. Now, the usual lore in the literature is that, well, determining this object is very bad. Why so? Because this is a matrix that is not known in principle as SL0 is not known in full generality, becomes larger and larger with the increasing of the level. Inverting that object is very inefficient. So like this is kind of the naive way in which one can construct OPE or blocks, but usually one gives up immediately because it seems hopeless. But the idea that we had is basically to determine an associated object, which we call like the index-free Shapovalov form, which is just the contraction of it with the generators. So L minus mu, SL, L0C, mu nu, L nu. Okay, so this is going to be the first object that we discuss, that we determine the new expressions for. Are there any questions?
So I should think about this really as a product of
Yes, it's a contraction of all the possible indices. We have a fixed level.
No, that I understand. I mean, I should really think about this expression as like a product of operators on a Hilbert space. It's not some, you're not missing some fancy tensor product science or anything here.
Well, it's just, yeah, it's a product of generators, indeed.
Okay.
Yeah.
So it's like an object in the, roughly speaking, universal enveloping algebra.
Exactly. We're going to see it's a generalization of the universal enveloping algebra, which is important. It's an important fact.
Well, it's some kind of completion because, sorry, what do you mean? Like you just wrote a definition. I should know which space it lives in.
Yeah, it's a universal enveloping algebra completed with basically functions of zero modes.
Of L naught.
Of L naught, yes.
Yeah, because, yeah.
Because
you
I'm
have
going to
to
just
divide
write
by
down
them,
immediately
yeah.
the expression that we got. I don't have time to make proofs or anything. But it's we're going to have poles, basically, which is expected.
No, yes, of course. But beyond that, that's just what it is.
Yeah,
right? Okay,
exactly.
Thanks.
So the result, again, I'm sorry, it is quite technical. So I'm going to have to write quite a bit. Can be written in an elegant form, but I'm going to have to explain what are the various objects that appear. QRS divided by L0 minus HR1 S1 LRS, again, vector, dagger. This is the expression of the resolution of the identity. What are these objects, though? Well, I introduced some notation in which we have RS vector, which is a vector of indices R1, S1 to Rm, Sm of a certain length. This basically can be seen as parameterizing sets of products of these singular vector operators, LRS, that make up a certain level L. Okay? So I'm going to have certain objects. This is a level R1 times S1, blah, 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 up to level Rm times Sm. And there are many ways in which one can take objects of this form to have objects of level L. Okay? This may be a bit complicated, but it's just ordered partition, so partitions with order, plus for every number, we have sets of singular vectors that we can have at that level.
Is it just tensors for writing up the homology relation?
It's not. It is very similar, but it's not. So we're gonna see that.
Keep it.
Now, LRS.
Sorry, before we proceed, can I also ask another question? Just, you're telling us various nice formulas about this object, but is it clear that this object is useful for anything? Like, can you reconstruct the resolution of identity from it or something like that?
Yes. Now, here you can see that basically the resolution of the identity is the sum over levels of negative mode contracted with this matrix, positive mode. Plus we have a projection, a projector in the middle. But that basically doesn't matter that much in the sense that if we define an expression of this, we just have to insert a projector in here, and we have the resolution of the identity and sum over levels.
But
in other words,
is this obvious? I mean, like, you're writing.
Why does this act as the identity? Maybe that's the question.
No. I understand why.
Okay.
What you wrote, why it's an identity. My question is, that's why I kept asking about whether this is literally in the universal enveloping algebra, right? Because you're writing this L minus mu on the left and L mu on the right, but then once I'm in algebra, I'm like allowed to commute them, like move this one to the left, this one to the right, and it's not obvious that after you do some manipulations on this formula, that inserting h in the middle of that formula is the same as inserting h in the middle of this formula.
Yeah. Okay. You have to be careful. Just the only important thing is not to act on the projector. As long as you don't do that, as long as you keep a prescription, which is to always evaluate on states once you have a normal ordering of generators, that you're gonna not have any issues. You're not gonna encounter issues. So in other words, this is an expression that you want to you can commute and you can reorganize. And you're allowed to act on states only when things are normal ordered.
I mean, it sounds to me like you actually don't want to define it to be universal in developing algebra. You just want to write some tensor product there and then keep it, and then it's fine. But yeah. Okay.
Well, the reason why I want it in the universal in developing algebra is because of the Casimir, actually. Because it's going to depend on this object, and the Casimir can be defined in terms of this Shapovalov.
Okay, let's maybe discuss afterwards.
Yep. Okay, basically we have the LRSs are just products of singular vector operators. The dagger just exchanges the order of this. And the QRSs are coefficients that we determined explicitly. Like these are products from I equal to 1 to m, Q Ri Si over product j equal to 1 to m minus 1 of h rj sj plus rj sj minus h rj plus 1 sj plus 1. There are some expressions that are like lengthy, so they take some time. What are these QRSs? They're inverse Zamologic of norms of the states LRS, HRS, regularized, so we divide by the 0. This is going to be 0 if we compute the scalar product of this with itself, by definition. But if we divide by the simple 0, we have the inverse Zamologic of norm regularized. It's something that is determined in the literature. I just don't want to write it because it takes time. Okay? This is to say, with this expression, we could prove it by induction, basically. We could show that we can show explicitly that at level 2 it works as the identity, and then higher level you can assume by induction, an inductive assumption, and prove that it works at L plus 1. Yes?
And you're assuming over all possible orderings of this
Precisely,
operators?
yes. Sorry, I didn't write equal to L. Yeah. All possible, so yeah, we basically have a vector of R's, a vector of S's. There is no order of them, so you can take any order possible, which is basically the same type of combinatorics that happens in Zamologic of formula, in fact. And then you indeed, you only have the constraint of the total sum of these being equal to L. Okay? The fact that this representation is kind of diagonal is surprising. Like, let me reiterate, this started from a matrix which is in principle very complicated. It's contracted with generators that, it's like contracting with different bases of vectors. Like, it's some kind of spectral decomposition of this matrix, of the inverse of the matrix, which is very non-trivial to achieve. And the singular vectors operators are the protagonists in this decomposition.
Can you just clarify the denominator the RS? No, in the S, yeah.
Yeah.
Not minus H1?
HR1, S1. So the pole only depends on the first one. Thank you. It was not clear. I did not say it. Okay. Now we determined a resolution of the identity. How am I doing on time, by the way? Okay. Here is the OP. Okay. Well, we can use the formula to work out an expression for the OP. This is going to be partially explicit, let's say, in the sense that it's going to depend on singular vector operators. But then when used for the expression of the blocks, it's going to be very explicit instead. Like, let me cut to the chase. We can insert the resolution of the identity that we worked out. On one side of the resolution of the identity, we're going to get some ratio of some 3-point function of this form. LRS, dagger, phi I, z, hj. We get this object. We can imagine of dividing it by the OP coefficient, hk, phi I, 1, hj. This is something that appears in the expression. And this object can actually be evaluated explicitly despite we don't know, without using explicit expression for the singular vectors, just by requiring compatibility with the fusion rules of Virasoro. So this is going to be some type of object. I'm sorry for all the notation that I'm introducing. I realize this was not maybe the best talk to give on a whiteboard with all the definitions. divided by some power of c, hi plus hj minus hk minus r dot s. Now this is, I'm saying that basically part of the action of this resolution of the identity, this part here, when inserted in here, produces a three-point object that one can evaluate explicitly. So the expression of the OPE becomes like the sum over the spectrum, let's say hk, of OPE coefficients, phi I1, hj, sum L greater or equal than 0, the same type of sum R dot S equal to L that appears in the resolution of the identity, of course, the same coefficients that appear in the resolution of the identity, hk minus hr1s1. I'm just copying so far the resolution of the identity. We have this object here inserted, so hk minus hj hi r s divided by what, that hi plus hj minus hk minus r dot s times L r s phi k of 0 evaluated at 0. Okay, what is not explicit here is this LRS, the expression for singular vectors. These are objects that are in principle complicated, as I mentioned. What is explicit here is this square bracket object. Definition on definitions. I'm sorry about this. What is this object? Again, it's defined in terms of these vectors, RS. So in principle, the definition is like modular, defined in terms of the individual pieces. Yes?
Can you give us a sense of how quickly the number of these vectors grows with the level?
It's fairly big, yes. But it's the same growth as, again, Zamolodchikov. It's at least, well, ordered partitions of level, but then the ordered partitions of the level you have to dress with how many singular vectors you have for every part of the ordered partition.
I'm just wondering if it's bigger, if it's faster or slower than the size of the Shapovalov form.
Then inverting like no.
I mean, the Shapovalov form is a matrix at every level, so it has some size, right? The number of descendants at that level. So I'm just wondering if it's faster or slower than this.
To determine the Shapovalov is probably slower.
No, sorry.
To determine the inverse.
I mean, instead of faster or slower, I mean more or less. Are there more these vectors of RS than there are descendants or less?
There are more. This is an overcomplete basis. So if we consider like the basis with the L muse, like that is integer partitions simply with an order, so Young tableau if you want. This is like ordered partitions, so you can also swap orders in the Young tableau, and you dress every singular row with the values of a singular vector. So it's definitely bigger. But to determine that object, in principle, you had to invert like integer partitions times integer partition matrix, which is like very complicated.
No. I understand that this is explicit. Just I'm wondering how many terms there are.
Yeah. Okay. But thanks. Now, what is this object? That is a product of J of some indeed a smaller object that one can define for every individual singular vector that is encountered in the expression. RASA. What are these ones here? These are very similar to the Zamolodchikov residues. If you're familiar with Zamolodchikov recursion relations, you're gonna probably recognize the form that they have. Like this is 0 and r minus 1, 0 and s minus 1. Momenta, pj squared minus pk squared plus L plus PRS squared minus pi plus pr minus 2m minus 1 s minus 2n minus 1 squared. This is basically a polynomial in the conformal dimensions, in the h's, that is just constrained by enforcing it to have zeros for all the possible, like any time that the diffusion rule has to be satisfied. The p's are simply defined in terms of the conformal dimension, like this. It's just a simpler way to express. In terms of the p's, has a nicer form. But this is very explicit. So this coefficient is very explicit. Having determined this explicitly allowed us to write down also an expression for the Virasoro conformal blocks that I'm going to write down here directly without any derivation. I realize I'm running low on time, which is like r dot s equal to L, again the QRS coefficients divided by h minus h r1 s1. And now we just have two copies of those square bracket objects. Rs, h minus h4, h3, rs, times cross ratio to the h plus level. Now, this is to say, like, from these computations, we could get like a very elegant formula for the Virasoro 4-point conformal blocks, which has, now let me just state some properties of it. It has explicit poles in H, like these are the same poles that one expects from Zamo logic of recursion relations. If one computes residues, one gets, for those poles, one gets exactly the same residues as Zamo logic of recursion relations. So these objects here are the Zamo logic of residues if we evaluate at singular vector conformal dimensions. But importantly, well, I already mentioned that the sums, the combinatorial sums, are the same ones as Zamo logic of recursion relation. But this is different than Zamo logic of recursion relation. Why? It is obvious to see from the fact that one has directly the dependence of h in the numerator. Zamo logic of recursion relation is a Mittag-Leffler expansion. One extracts residues iteratively. So nothing in the numerator can depend on h. So this is different from that, has the same complexity of it, but has some different properties which may be beneficial in certain cases. For example, if we want to evaluate conformal blocks at for minimal models, or in general for degenerate representations, we have that normally one would be worried about these poles here, so h minus hrs, that could blow up. But the way these objects are constructed, these are constructed to have zeros at the values where the fusion rules are satisfied. So whenever we take a degenerate block, this just gives the correct answer because of the double zeros in the numerator. So the poles are not a problem. The fact that we have some modular structure, like the dependence on this symbol is like factorized in terms of the RSs, makes it possible to recycle a lot of terms, in principle, when one computing higher level terms. So this is, in principle, I believe it is an efficient formula numerically. I would like to compare it with the Zamo logic of recursion. And finally, concerning the blocks, we could evaluate explicitly this formula at large C, connect to the global conformal blocks for SL2R, and also get some leading asymptotics for the semi-classical limits, actually, because one can study the behavior of these coefficients, one can see what are the terms that lead, and we can get the first terms in the exponentiation of semi-classical blocks, for example. So this is all for the blocks. Probably I'm out of time, so I don't know if I can discuss the Casimir. Yes. All right. So the Casimir operator, simply, what did we do for that? We started with the question, can one determine a Casimir operator for Virasoro? Like, what is a Casimir? It's an object that commutes with all of the generators of the algebra. So we want some object C that commutes with the LM and gives us 0. This object is useful in higher DCFTs because like it measures the conformal dimension of a whole conformal multiplet instead of just the primary. and one can work out the differential equations, and it's very useful. For the case of Virasoro, this has to be an object with the form like a sum over all levels, L minus mu, some coefficients, ML, L0C, mu nu, L nu. And just by requiring commutativity with the generator of Virasoro, that's just the dumbest thing you can do. You just require that. Well, I shouldn't say dumb because this was like already stated by Feigin and Fuchs in 83. But like this is a naive approach to do. It actually works. Feigin and Fuchs wrote some recurrence relations. They got to some conclusions that I personally disagree with at some point. If you want, we can discuss about them. But what we did, in addition to Feigin and Fuchs, we solved the recurrence relation. And we got an expression of the Casimir operator in terms of the inverse Shapovalov form, like the one contracted with the generators of Virasoro, and which depends on an arbitrary function, on the arbitrary coefficient at level 0, which, for example, we can choose to be L0 times L0 minus 1. And it's an infinite order Casimir. At large central charge reduces to the SL2R Casimir, so it's all compatible with that. And it's an interesting object because like it's very unexplored, very much unexplored. I wonder what are its properties. It's non-local because it involves infinitely many terms, infinitely many generators, and like it's an infinite order object. One can define, in principle, an infinite order differential equation whose eigenfunctions are known explicitly. And a similar type of object has been considered as a candidate action for string field theory. So it may have also an application within that context. But I'm out of time, I think, so I probably shouldn't add much more. Thank you very much.
So you said you can start, like there is an arbitrary function of L naught in the beginning. So in some sense you get infinitely many Casimirs.
Exactly, but only one is independent. Like because you can take a function of an infinite order object, it's going to be still an infinite order object, and it's still going to be a Casimir because of if the initial one commuted, then the next one commutes.
I see. So just one question about so you said you wanted to compare, this formula for conformal block with the Molotchikov, and one obvious problem with your formula is that your formula is an expansion in X.
Yes.
So can you go to this fancy geometry and do the calculation there so that you get it in expansion in the gnome in the Q?
Good point. Not yet so far. Like the main reason why we could get an expression for this was because we could determine this coefficient explicitly just by comparing with the fusion rules and having an explicit action of the differential operator associated with the singular vectors. It's not yet clear to me how to construct that in the pillow geometry that's relevant for the gnome variable for Zamolodchikov, but I do wonder indeed. I thought a bit about it. I never actually tried, so I don't know about that. But it's just what I meant by comparing with Zamolodchikov is just like efficiency. Like if one can actually, if one wants to work in cross ratio space, say in X space, so one would have to convert back. So it's probably unfair comparison. But how quickly one can evaluate.
Good question. The Casimir commutes with positive frequency or both?
The Casimir commutes with anything, with all of the generators.
So okay, the Casimir commutes with anything.
Yes.
Thanks.
Other questions?
And it becomes a finite order if you look at the minimal series values.
Minimal series of values. What do you mean?
There's the minimal model charges. Does the Casimir become finite order? Is this like a?
You mean
a
acting
compact
on
formula for all the null equations for minimal models?
On its own, it's gonna be an object that depends still on L0. So I don't imagine to have
No, but L0 also, you would fix it to one of the singular vectors. and
Yeah, but at that point, you're evaluating already the Casimir on some state, so that's just going to give you an eigenvalue. So you don't have much to do if you're already thinking of acting on a state.
I'll ask you after.
Okay.
John?
Yeah.
Can you? I'm curious that the Virasoro crossing kernel is known. Is it clear if you integrate it against your representation of the conformal block that you find say the T-channel block?
The answer is it's not clear.
It's
Like,
not clear, okay.
but it would be interesting to see if it is. Like,
But it's not
one.
obvious. It would be
No. To me, no. At least not so far.
Thanks.
Okay, then I have a question. Let's take Lorenzo.
Thank you.